Welcome to the AWS routing video in the Cisco Secure Firewall in AWS video series. Hybrid Mesh Firewall is a new market category that focuses on unifying physical, virtual cloud, and agent-based enforcement points to simplify security operations. The intended audience for this video is anyone who wants to better understand hybrid mesh firewall solutions. Also, network security practitioners who want to extend their skills into the public cloud, and cloud practitioners who want to better understand how security is deployed across multi-cloud and hybrid cloud environments. And frankly, anyone who wants to have a better understanding of AWS and firewall deployments in the public cloud. The objective is to provide a detailed understanding of AWS routing. Prerequisites are a basic understanding of network technology and network security, at least for physical networks. It also assumes the knowledge given in the fundamentals and architecture videos of these series, or comparable understanding of AWS fundamentals. We start with a discussion of physical versus AWS networking. We then give simple examples, VPC peering and transit gateway routing. We then have a more elaborate example of the routing deployed by Cisco Multi-Cloud Defense. And we conclude with a discussion of ingress routing. The public cloud is easy to learn. Step 1, forget everything you know about networking. This, in fact, is quite accurate. Although public cloud networking is confusing when you first work with it, it's actually far simpler than enterprise networking. Here are some key differences. First of all, how static routing works. Static routes are configured on devices in a physical network. In the cloud, static routing is primarily handled by the cloud infrastructure. The devices really only determine the egress interface. Once the traffic exits the VM, the routing is handled by the AWS infrastructure. In physical networks, a next hop is always an IP address, and devices determine the next hop for given packets. In AWS, the next hop is an AWS object, and the AWS infrastructure determines which object that the packet is forwarded to. Dynamic routing can be quite complex in physical networks where you have an interaction of multiple routing protocols, and pretty much any device can participate in the dynamic routing. In AWS, dynamic routing is really only BGP, and it's quite limited which devices are permitted to do what with BGP. Let's start with a very simple VPC peering example. Imagine that we have two VPCs that communicate to the cloud independently, and we want to set up east-west traffic between them through a VPC peering connection. The next hop is going to be the VPC peering. You're not allowed to have a next hop be a device in a remote VPC. And if you think about it, this means that there's really not a good way to insert firewall into this topology. Furthermore, the topology does not scale well. It requires quadratic growth in VPC peering connections relative to the number of VPCs, but it serves as a really good example of simple AWS routing. And the way we're going to do this is by following the packet and look at east-west traffic in particular. We're going to start in the VPC dashboard. Let's look at the routing table for the first application. Notice that the default route is to the internet gateway and the local traffic is local. And the key route here is that we have a peering connection for the remote VPC. Notice that the choices for next hop are objects within the AWS architecture. At first, it looks like this route table is not used by any subnet, but this is a main route table. So by default, it's used by all the subnets in the VPC. There are no edge associations or route propagations. If we look at the second VPC, we see a similar routing configuration. Let's now look at a simple example of transit gateway routing. In this case, our VPCs are connected to a transit gateway for east-west traffic, and we've also thrown in an on-prem data center with a firewall that's going to be attached to the transit gateway. We're going to use both static and the dynamic routing here. This is quite suitable for east-west firewall insertion by adding a service VPC, as we will see in a subsequent example. Here we have the routing for the first VPC. Notice the default route points to the Internet Gateway. There's a local route, and then we have 3 routes that point to the transit gateway. This is for the traffic to the other VPC and to the on-prem networks. We are not propagating routes here, and there are no edge associations. Everything is done with static routing. When we send the traffic to the transit gateway, the transit gateway route table is associated with all the transit gateway attachments. If we look at the routes, we'll see that we have routes to the various components of our hybrid network through the transit gateway or through the VPN attachment. It looks like we have 2 attachments there, but if you look carefully, it's the same VPN attachment. It's simply that AWS by default utilizes dual tunnels within any site-to-site VPN for redundancy. Notice that in this case, we are using propagations. So we didn't have to set up the routes. If you look more carefully at those routes, you'll notice that they were all propagated. This is actually under the hood BGP. And here on our on-prem firewall, we can see the BGP routes to the 2 VPCs advertised via AWS, as well as the static routes that we advertised to AWS. Let's move on to a more complicated example. The routing deployed by a product called Cisco Multi-Cloud Defense. Cisco Multi-Cloud Defense is a firewall orchestrator built into the Cisco Security Cloud Control. It dramatically simplifies Cisco Secure Firewall insertion into multiple public cloud environments, unifying and simplifying the deployment. It operationalizes maintenance, automatically scaling in and out to adjust for load. It also monitors the health of the Cisco Secure Firewall and replaces unhealthy units. It also performs upgrades and downgrades. In the green rectangle, you'll see all the components of the public cloud that are orchestrated by Cisco Multi-Cloud Defense. So in principle, you don't have to understand AWS routing to use Multi-Cloud Defense in AWS. However, it serves as a very nice example of routing. Notice that it deploys a transit gateway, and in a service VPC, it deploys a gateway load balancer endpoint, which will forward the traffic to the gateway load balancer and then to the Cisco secure firewalls. This is a so-called 2-arm deployment. Traffic destined for the internet will be sent through an internet gateway, thus giving you a unified egress, whereas east-west traffic will be forwarded immediately back to the gateway load balancer to the transit gateway, where it will be forwarded to the target VPC. We'll focus primarily on this east-west traffic and again, follow the packet. Let's start with the route table in the first application VPC. You can see the default route is to the transit gateway. So that means that we're going to use transit gateway routing to figure out what's going on. Let's go to that attachment and let's look at the associated transit gateway route table. And we'll actually see, if we look at the routes, that all traffic is forwarded to some attachment. That's the attachment of the service VPC. That is associated with a subnet, which has a route table, which determines where the traffic is forwarded at that point. If we look at that route table, we see that the traffic is forwarded to an ENI. Well, what is that ENI? That ENI is a gateway load balancer endpoint. Once the traffic is processed by the firewall, it is routed based upon the route table associated with the gateway load balancer endpoint, which says to send the traffic back to the transit gateway. Once it's received by the transit gateway, the attachment from the service VPC is utilized, and it has a transit gateway route table. That transit gateway route table says to return the traffic to the appropriate VPC. Once it arrives in the VPC, it uses the transit gateway subnet that's associated with that VPC attachment. That subnet has a route table, and that route table has a local route which will deliver the traffic to the appropriate VM. Let's conclude with a simple example of ingress routing. If we want to inspect inbound traffic from the internet, we will have to send the traffic as it arrives at the internet gateway to the gateway load balancer endpoint. This has to override the default, which would be to send it to the application whose public IP received the traffic. Such an override requires what is called ingress routing. In this case, the firewall is configured as a one-arm deployment. Once it receives the traffic through a private link, it will simply return the traffic to the gateway load balancer, where the traffic will be returned to the gateway load balancer endpoint. Thus, we think of the gateway load balancer endpoint as a step in the traffic where both ingress and egress traffic are intercepted and sent for inspection. We have created a subnet, and this is the subnet that's going to be associated with the endpoint. Let's install the endpoint. First, we have to find the endpoint service for the gateway load balancer, and then we can utilize that to configure the endpoint. Notice we choose the appropriate type of endpoint, and we put the service name there. We associate this with the subnet that we created in the first application VPC. Currently that's pending, but it will soon come online. Since we're building on the last example we did, we first have to make a change to the route table for the first application VPC. Currently, if we look at the routes, the default route is pointing to the transit gateway. We want to actually change that so that the default route points to a gateway load balancer endpoint in our VPC. This will intercept the outbound packets and send them to the gateway load balancer endpoint. This is the subnet that traffic will utilize after inspection, and therefore we need a separate route table to handle this traffic. Otherwise, we would get a routing loop. So let's create a route table. We're going to associate this with the application VPC. And let's explicitly associate this with the gateway load balancer endpoint subnet. Local traffic should be delivered locally, but we have to think a minute what we want the default route to be. Since the traffic will have already been processed by the firewalls, we want to send that traffic out to the internet. So we set the IGW to the next hop for the default route. Let's actually configure the ingress routing. We could do this with an existing route table, but it's probably best to have a separate route table just for ingress routing. Ingress routing utilizes what's called an edge association. Notice that we can choose the Internet Gateway as an edge association. Other edge associations would be, for example, VPN attachments. And rather than sending local traffic locally, in other words, directly to the VM, we're going to send it to the gateway load balancer endpoint. This will intercept the traffic and inspect the inbound traffic. And that is all we really need to do to configure ingress routing. Thank you very much for your time.